Guys, so for today, we are going to continue our discussion all about the part 4 of the 1001 integrals by yours truly, Engineer Jei Abat. So, let's get started. Okay, so how do we integrate this given integral? The integral of cosecant squared y, okay, multiplied by the square root of 1 plus 3 cotangent y dy. This is none other than a simple u substitution because as we can see, we have a cotangent in here and the derivative of a cotangent is negative cosecant squared. So if we are going to let u the function that is inside the square root, we have 1 plus 3 cotangent of y, get the derivative of u with respect to y. So we have 0 for the derivative of 1 and then we have plus, or I mean that becomes minus because of the derivative of cotangent. So let me just put plus here. So the derivative of cotangent is negative cosecant squared y, and that is in terms of dy. So positive times negative becomes du equals negative 3 cosecant squared y dy. And in the given integral, I have the cosecant squared y dy such that if I'm going to rewrite this would look like this: 1 plus 3 cotangent of y multiplied by cosecant squared y dy. So I have this term here. So I can isolate cosecant squared y dy so I can have it substitute in the given integral. So we have du all over negative 3 equals cosecant squared y dy. So by u substitution, we can simply substitute this. So we have the square root of 1 plus 3 cotangent y, we let that as our u. And then our du, our cosecant squared y dy, here it is, and that is in terms of du, that is du all over negative 3. So I can factor out the negative 1/3 outside of the integral sign. Then we have, I'm going to convert this rational expression in terms of exponential. So that square root, that's u raised to 1/2. And then we have du. So this is a simple power formula. We have 1/2 plus u all over 1/2 plus u. Plus 1, I mean. So we have u raised to 1/2 plus 1 becomes 3/2 all over 3/2. And then we have plus c in here. Simplifying, I'm going to get the reciprocal of this. So we have negative 1/3 times 2/3 u raised to 3/2 plus c. Okay? And so by simplifying, we have the answer negative 2 all over 9. Okay, replacing or substituting back the value of u, wherein our u is 1 plus 3 cotangent y. So that becomes 1 plus 3 cotangent of y raised to 3/2 plus c. And that is our answer for this problem. So continuing with our number 32 problem. For number 32, we have the integral of secant x tangent of x dx all over, we have 3 plus 4 secant of x raised to 1/2, 3 plus 4 secant of x raised to 1/2. So how do we integrate this? Okay, so upon looking at the integral, on the denominator side, we have 3 plus 4 secant of x raised to 1/2. And if we are going to look at it carefully, the numerator has a secant of x tangent of x, right? So if we are going to let you the denominator 3 plus 4 secant of x, we will be having a derivative in terms of secant of x tangent of x, because the derivative of secant of x is secant of x tangent of x. So let's try to have this as our u, the 3 plus 4 secant of x. So if we're going to get a derivative of u with respect to x, that would be 0 plus 4. The derivative of secant of x is secant of x tangent of x dx. So we have du equals 4 secant of x tangent of x dx. And on the numerator, I have secant of x, tangent of x, dx. So which means I'm going to isolate secant of x, tangent of x, dx here. And I'm going to divide this by 4. So we have du all over 4, secant of x, tangent of x, dx. Okay, so what we're going to do is we simply substitute it. So we have secant of x, tangent of x, that's du all over 4 all over 3 plus 4 secant of x, of which we let that as our u. That should be raised to 1/2 because of the exponent here. So factoring out the constant, 1/4, we have the integral of du all over u raised to 1/2. But of course, we can use power formula here by using the properties of exponents, wherein we are going to get the reciprocal of this denominator, but we are going to negate its exponent. So we have u raised to negative 1/2 du. And that is a power rule. So that would be 1/4 u raised to negative 1/2 plus 1 all over negative 1/2 plus 1. So negative 1/2 plus 1 would become positive 1/2. And this would be 1/2 also. Okay? So simplifying, we have 1/4 getting the reciprocal, 2 all over 1. U raised to 1/2 plus c. So we have 2 all over 4, that's 2. Okay? So we have 1 times 1. This becomes 1. 1 times 1 is 1 all over 2 times 1 is 2. We have u raised to 1/2 plus c in here. Okay? But we have to substitute back the original value of u. So u is equal to 3 plus 4 secant of x. So we have 1/2 multiplied by 3 plus 4 secant of x raised to 1/2 plus c. And that is our answer for this given problem. Okay, moving on to our third example. For our third example, we have the integral of cotangent of beta. Okay, and then we have ln of sine beta d beta. Okay, our variable here is the beta. We are integrating with respect to beta. Of course. Okay. So this may seem kind of little bit hard. Okay. But actually, it's not. We have an ln function in terms of ln of sine beta, and then we have cotangent beta. If you're going to rewrite this, we have ln of sine beta and cotangent beta d beta. So we cannot use any any trigonometric identity here because the sine is inside the ln. So most probably that this would be a simple u substitution. So if we're going to let u equals to the ln of sine beta, and we're going to get the derivative of u. Take note that this is in ln. So in order for us to get a derivative of ln, that's du all over u. So we have to get whatever is the derivative of the inside the ln. And the derivative of sine beta is cosine beta. Let me just change my pen. That's cosine beta all over. We have what? We have the original u, which is sine beta. That's how we get the derivative of the ln. Okay? So that is with respect to the beta. Of course, from our trigonometric identity, we know that cosine theta all over sine theta, and that is equal to cotangent theta. That is the same scenario with what we have gotten when we differentiate the u with respect to beta. That's cotangent beta. So cotangent beta d beta is here. So we can replace this as du cotangent beta d beta. So this is none other than a simple u substitution. So if we're going to substitute, we have ln of sine beta, that is our u, okay? And cotangent beta d beta, that is our du. So simply, we're evaluating the integral of u du, and that is simply u squared all over 2 plus c. Or in other words, we have 1/2 u squared plus c. We have to substitute back the value of u, and that is ln of sine beta squared plus c. Okay? Or in other words, we have 1/2 ln of squared sine beta. That is the same as this one. Still the same. So that is our final answer for this given integral. So it's a matter of experience on how we are going to solve the given integral. Okay, if you solve more of the integrals, then you will be able to solve the integrals much easier if you solve problems every day. Okay, so if you want to be good at math, there's no other way but to just solve and solve and solve and solve. So for our next problem, for our fourth problem, we have the integral of 2x plus 1. We have dx all over. We have x plus 2 times x minus 1 raised to 4. So again, if we are going to look at this integral, okay, this must be a u substitution, because there is a great chance that this would be a u substitution because we have something in our denominator or in our numerator. So let's try to simplify first the denominator. So if we're going to perform FOIL on x plus 2 and x minus 1, we know that is gonna be x squared, okay, first, then outer minus x, then inner plus 2x, and then last minus 2, and raised to 4. So let's try to simplify this. 2x plus 1, we have dx all over x squared plus x, okay, x squared plus x minus 2. So I have x squared plus x minus 2 raised to 4. Don't forget to write the raised to 4. So and again, as you can see, if we are going to let u, the denominator, we have x squared plus x minus 2. Get the derivative of that. That would be 2x plus 1. Of course, this is with respect to dx. So 2x plus 1 dx is readily available on the numerator. And then we are going to perform the u substitution. So 2x plus 1 dx is simply du, and that is all over x squared plus x minus 2, and that we let u, and then we have raised to 4. So this is simply as u raised to negative 4 du. That is simply a power formula. So we have u raised to negative 3 all over negative 3, because negative 4 plus 1 is negative 3. So plus c. So we have negative 1/3 u raised to negative 3 plus c. Okay, but I would like to substitute the u back. Okay, so I'd like to substitute the u back to its original variable, and that is x squared plus x minus 2 raised to negative 3 plus c. This can be our final answer, but it's good if we can eliminate, okay, the negative 3 here in our exponent. It's more neat. So we have x squared plus x minus 2 plus c. Or in other words, you can write it as, let me just here. Okay, so we use the properties of exponent to eliminate the negative exponent. But which of which, whether this one or this one, that is still the same. I'm just used to eliminating the negative sign in the exponent, so as to make our equation more neat. Okay, so let's try again another problem. For number 35, we have the integral of tangent of alpha d alpha, okay, all over 1 plus ln of cosine alpha raised to 3/2, if I'm not mistaken. That is 3/2. So how do we get the integral of this? It's very simple. Again, in these cases wherein we have a trigonometric function, we have to consider always if there is a trigonometric identity involved. But then, upon looking at this is simply a U substitution. Okay? So, in order for us to clearly see this, we can convert tangent theta, and that is equivalent to sine theta all over cosine theta. The reason behind doing this is because if we get the ln of the derivative of ln, that is negative sine all over cosine. Okay? So, we can use a U substitution. So, for now, we have what? 1 all over 1 plus ln of cosine alpha raised to 3 halves multiplied by the tangent alpha d alpha, and I'm going to convert that into sine alpha all over cosine alpha d alpha. Okay? So, furthermore, if I'm going to let u, the numerator, so we have the denominator, I mean, with 3 halves, 1 plus ln of cosine of alpha, the derivative of that, this would become 0, of course. The derivative of ln cosine alpha would be the derivative of cosine alpha, that's negative sine alpha, all over the original itself, cosine alpha. And that is in terms of the alpha. So if you can see, sine alpha all over cosine alpha, which is actually what? That is actually what we are trying to look at it. Okay? And that is our du. So if I'm going to isolate, I have sine alpha all over cosine alpha d alpha here. So I'm going to isolate this one by multiplying both sides by negative 1. So we have negative du equals sine alpha cosine alpha d alpha. I can perform now U substitution. So if I perform U substitution, that would be integral of 1 plus u raised to 3 halves, of course. And then we have sine alpha all over cosine alpha d alpha is simply equal to negative du. So I have negative du here. I can factor out negative outside of the integral sign, so that we have, I can raise this into negative, get the reciprocal of that. By properties of exponent, I can negate the exponent and make this u as my numerator. So we have u raised to negative 3 halves multiplied by du. And Viola, that is simply a u power formula. Negative 3 halves plus 1 would be negative 1 half. U all over u raised to negative 1 all over negative 1 half, and then plus c. So getting the reciprocal, so we have negative 2 all over 1, u raised to negative 1 half plus c. And then we have negative 2, negative times negative, that would be 2. Okay, so we have 2 u raised to 1, negative 1 half plus c. So I can bring this downward by negating its exponent. The negative of the negative 1 half, it will become 1 half plus c. Well, of course, if you're going to substitute it back, so we have 2 all over u. What is the u? The u is actually 1 plus ln of cosine of alpha. Of course, this is raised to 1 half. Okay, that is raised to 1 half plus c. That will be our final answer for this. Okay, for our number 6 problem, we have number 36. Okay, so we have 36 as the integral of cosecant, hyperbolic cosecant squared y and hyperbolic sine of y dy. So this is none other than a simple U substitution, of course. Okay, this is not cosecant, I mean. This is hyperbolic cosine squared y. So this is none other than a simple U substitution. So we can let u as hyperbolic cosecant y. Then our du is the hyperbolic sine y di. Take note that the derivative, of course, this would be not squared. We will not be including the squared. So we have hyperbolic cosine of y, And then the derivative of that is hyperbolic sign. So there will be no negative, unlike the trigonometric derivative, right? Because the trigonometric derivative, let's say cosine, the derivative of cosine is negative sign. But here in hyperbolic, if we wish to recall that the derivative of hyperbolic cosine is simply positive hyperbolic sign also. So that is simple, is use substitution as that. So we let u as hyperbolic cosine y, so we have u squared. Then we have hyperbolic sine of y dy, that would be du. This is simple as power formula. So we have u raised to 3 all over 3 plus c. And if we're going to look at it, we have the answer 1/3 going back to our original value of u, or u substitution, original value or variable. So I have cos hyperbolic cosine cube of y, and then we have plus c. That is how simple we actually solve this given integral. Okay, so that is for our number 6. So for number 7, we have another, for number 37, we have another hyperbolic function involving our integral. So you have the hyperbolic sine of 3w dw all over, we have 1 plus 4 hyperbolic cosine of 3w raised to square, or square. So this is none other than a simple u substitution again, because if we let u 1 plus 4 hyperbolic cosine of 3w, get the derivative of u with respect to w. So we have 4. The derivative of hyperbolic cosine is sine hyperbolic sine 3w. And of course, we have to differentiate the inner function. That is a chain rule. So we have 3 with respect to w. So we have dw. So we have du, 4 times 3, that's 12, hyperbolic sine of 3w. So I have an available hyperbolic sine 3w dw on my numerator. So I can simply isolate this one to simply perform the u substitution. So we have du all over 12 equals the hyperbolic sine of 3w dw. So we are now ready to perform u substitution in this given integral. So we have sine hyperbolic sine 3w dw equals du all over 12. So that must become du all over 12 all over. We have let this 1 plus 4 hyperbolic cosine 3w as our u. So we have u squared here. So we have 1 all over 12. We can factor out the constant, and then we have du all over u squared. Then by properties of exponents, so we have u raised to negative 2 in du. That is just simply a power formula. That becomes u raised to negative 1, negative 1. So we have negative 1 all over 12. And then we have times u, of which the u equals 1 plus 4 hyperbolic cosine w raised to negative 1 plus c. This can be our final answer. But to make it more neat, okay, we have to eliminate the negative 1 here by getting its reciprocal. So we have negative 1 all over 12, 1 plus 4 hyperbolic cosine of w plus c. So this could be our final answer, thus eliminating the negative exponent in our given formula. Okay, so for number 38, okay, so we are performing 10 problems, of course. So for number 38, we have to get the integral of 2 dy all over 3y minus 4. It's a very simple integral, right? So in evaluating the integral of this, make sure that we follow the properties of integral. We can factor out 2 outside of the integral, and then we have dy all over 3y minus 4. So if we do that, we can use u substitution. We're going to let u as 3y minus 4, then the derivative of u with respect to y would be 3 dy. Okay, get the derivative of this with respect to y. This negative 4 would be 0, and the derivative of 3y is simply 3 with respect to y. So I have dy on my numerator. So I only want to isolate dy on the right side of our equation. So you have du all over 3 equals dy. So I can now perform the u substitution because we have to integral of the dy, which is du all over 3 here. So we have du all over 3 3y minus 4 is u. So I can factor out again first the 1/3 outside of the integral sign, and I have integral of du all over u. And you know it, the integral of du all over u is simply what? Ln of the absolute value of u plus c, wherein our value of u should be changed into its original variable. We have let that as our 3y minus 4. So that would be 2/3 ln of the absolute value of 3y minus 4 plus c. And that should be our correct answer. Final answer for this given problem. Okay. So that is how we do it. Okay. So for number 9, second to the last problem that we have today. So for 39, we have the integral of x squared dx all over x cubed plus 4. Well, of course, if we're going to clearly look at the integral, this has a cube and this has a squared. So most probably, this would be a u substitution again. If I'm going to let u x cubed plus 4 and derivative of u with respect to x, that's 3x squared dx. I have x squared dx on my numerator, so I only want x squared dx here. So you have du all over 3, and then we have x squared dx here. So if I do that, I can use my u substitution. I have x squared dx that is simply equal to du all over 3, and that is all over the u. So I can factor out 1/3 outside the integral, and then we have du all over u. Okay, that would again result to a natural logarithm answer. So we have 1/3 ln of the absolute value of u plus c. So substituting back the value of u, that is x cubed plus 4 plus c. So this could be our answer. So some of the books or some of the references would actually write this as our answer, as our final answer. This is still correct, okay? Because there is a property on natural logarithm wherein, for example, you have 2 ln of a. We can rewrite it as ln of a squared, wherein whatever is the value of the constant value of the ln, it becomes the exponent of whatever is inside the ln. So this becomes ln of a squared. Same process that what happened to this. This 1/3 becomes the exponent of whatever is inside the ln. So that's how you write it at the other way, the answer. So for our last problem here, on our part 4 of integrals, 1001 integrals, so we have 40. Number 40, we have v dv all over 6v squared minus 1. If we are going to look at it again, we might think that this is a partial fraction, but it's not. Actually, this is a simple u substitution because we have v squared and then we have v on the numerator, so we can let u equals 6v squared minus 1, then get the derivative with respect to v, that is 12v dv. Okay, by power rule. So v dv, we have v dv here. I can isolate v dv here, so du all over 12, and then we have v dv. And that's it. We can now simply substitute v dv, it's du all over 12 all over 6v squared, that is our u. Okay, so what are we going to do? Here we are 1 all over 12 integral of du all over u. Okay, so we have a natural logarithm again. So ln of the absolute value of u plus c. Don't forget to substitute it back to its original variable, the u. So we have 6v squared minus 1 plus c. This could be the answer. Or, again, just like what I've told you, we have ln of the absolute value of 6v squared minus 1 then raised to 112 plus c. That would be our final answer for this given integral. Okay, so thank you so much guys for listening. I hope you still you learned from this video. And please, if you're new to my channel, please don't forget to subscribe. I have many videos about integrals, about the techniques of the integrals. This is only a part of my advocate, of which I'm helping students to be not afraid in integrals by solving 1001 solved integrals. Okay, so thank you so much guys for listening. Again, this is Jei Abat. See you again on the next video. Bye. God bless.